Hi everyone. My name is Teamah, and I am working as a professor within the Department of Building Science at Algonquin College Center for Construction Excellence in Ottawa, Ontario, Canada. Today I will be presenting our paper, which is entitled Experimental Investigation of the Effectiveness of Dynamic Fenestration Insulation in Canadian Climate. This was a capstone research project finding for the final year students who are listed here: Neil MacDonald, Aman Gupta, Alicia Houle, Jasmine Marston, Bailey Armstrong, Gabriela Aguilar, and me as a supervisor for them. So our work was basically done experimentally on investigating the dynamic fenestration insulation in the Canadian climate. So I will be first going into an introduction and why this work is important. So I will be covering an introduction. What is the objective of what we are trying to do? What is our methodology, the results and the conclusions and recommendations out of our work? So first of all, greenhouse gas emissions has been a serious issue not only in Canada but across the whole world. So everyone is caring about the climate change, and we wouldn't be able to reduce the extent and the adverse effect of climate change without looking into the main sources of greenhouse gas emissions. So the greenhouse gas emissions are really concentrated in a noticeable percent in the building sector. So as we can see from here, we have the building sector constituting a good portion of the greenhouse gas emissions in Canada. The majority of greenhouse gas emissions in the building sector are basically in space and water, heating, and other resources within the end uses of the building. So if we look at the building envelope, like what we can see here, you will find that a lot of greenhouse gas emission will be throughout different portions of the building envelope, whether it is the walls, whether it is the roof, the windows, and the leaks, and the floor as well. And the thermal imaging is always able to show that there is thermal bridging and a lot of heat losses that happens in the building envelope. So if we look at our 2050 targets, which is bringing net zero greenhouse gas emissions, as Canada is committed to this, according to the global agreements, this will never happen without trying to decarbonize the built environment. So we need to take care of space heating because it is a leading source of energy consumption and the greenhouse gas emissions within different buildings. So people started to say we need to reduce heat losses, and researchers have been concentrating on reducing heat losses throughout the building envelope. Reducing the heat loss within the walls has been reported a lot in the literature, and it is typically done by adding a better insulation with high IR values. However, in case of windows, a lot of people have in the research community has addressed it through low emissivity planes and also adding inert gas to fill the gap in between those window panes, as has been reported in the literature. However, there isn't that much analysis on other innovative technologies in order to reduce the heat losses throughout the window system within a building. This is why the National Research Council of Canada started to publish a report that analyzes the fundamentals of applicability of window shutters. So the window shutters are investigated, but not in cold climates like Canada that we are taking into account in this paper. However, it has been researched outside Canada, which has motivated the National Research Council of Canada to investigate its viability in the Canadian climate. However, from their recommendations, they said that there needs to be more investigations to make sure that the feasibility is making sense, and an experimental investigation is really important in order to make sure that those window shutters are really suitable for the Canadian climate, especially with its very cold winter weather. So our objective stemmed from this gap of the research. So we are looking at researching effectiveness of external insulated window shutters to control the heat loss in a Canadian climate. To do this, we have done an experimental setup on a test shed, which is located at Algonquin College, Ottawa, Ontario, Canada. So as we can see from here, this is the location of the shed. It is located in one of the buildings of the college, in the visitors parking, behind the visitors parking. And this is the panel construction process that was added to the test shed. So we will be looking at this shutter added to this panel, how it will affect the heat losses and the thermal imaging. So to test our hypothesis and to do the main data collection, we had to very first build the panel, which is the total panel that we are seeing on the right hand side here, with a window and attaching it to the existing shed like what we can see from here. Then we were able to add the insulated window shutter like what we are seeing here and attaching it to the panel. We took thermal images for the shed and for the shed in case of having this window shutter opened or closed, and we compared the performance of this the thermal performance for the case of with and without the shutter. So more details about the panel assembly. So the panel assembly, as we can see from here, is this is the panel assembly and the cross section of it. So the panel assembly is consisting of 2 by 6 framing, and there is a thermal insulation, which is bad insulation in the cavities, the pink ones that we are seeing from here, and the half-inch plywood sheathing as a structural support on the interior and exterior sides that we are seeing. There is also a vapor barrier of 6 milli poly and also Tyvek air barrier as vapor and air barrier for such panel wall as we can see from here. So we can see this panel assembly with framing and the matte insulation. And after that, this is when the window was installed into it. So this is the panel assembly finished with plywood, window, and spray foam insulation in order to make sure that we prevent the leak that is here. Then we go into the shutter and how it was added to our test system. So as we can see in the images, the dynamic shutter was attached to the assembly and secured by wood cuts, as we can see from the images, with a hinge on one side and a latch on the other. The shutter assembly consisted of plywood sheet attached to 2-inch XPS rigid insulation board, like what we can see from here. The rigid insulation is then overlapped with the exterior of the window, which has a silicon gasket weather strip to prevent air leakage, like what we are seeing here at the sides of the window. So we reduce the leakage as much as we can. So this is the closed position, and this is the open position of the window shutter. To collect the data, we had to insert 7 Kestrel temperature sensors in different locations in order to track the changes in the temperature. So this is the outdoor temperature, this is the indoor temperature, this is the outer surface of the shutter, this is the inner surface of the shutter and the window respectively, and what happens throughout the wall. So the data was collected for a week with the shutter open 24/7. So in this case, the shutter wasn't included. It was also collected for another week where the shutter was open at sunrise and closed at the sunset, and the data was tracked by the sensors and exported as Excel files like what we will see from here. The data was actually taken in the month of February. So it was in a cold weather in order to make sure that the heat loss is the highest it can be. So we are able to really get a good hypothesis of is this shutter effective or not. So from the results, we can see from here that we have the window and the exterior temperature when we have no shutter, and we have the window and the exterior temperature when the shutter is closed. So like what we see from here, this is the indoor window temperature, which is the yellow that we can see from here. The gray line here is the outdoor window temperature. The outdoor temperature is the light blue color that we are seeing from here. So in case that we have the shutter open, you will find that there is a very large gap between the yellow and the gray lines here. However, when the shutter was closed and was taken into account, you will find that this gap is less, as we can see from here, between the yellow color and the gray color. So it means that there is a stabilization of interior window temperature when the shutter was shown. And this is how we can see it from the thermal imaging. There is a stabilization in the difference in temperature that we are seeing in case of without shutter relative to the with shutter here. So between 11 and zero point 0.8, the temperature difference is a lot high relative to between 14.4 and 9.5. So the magnitude of temperatures became higher with the thermal imaging in the case of installing the shutter, and also the temperature variation is also becoming less when we have the shutter. So it is warmer in temperature, and also the temperature difference is not as high. We can also see another tracking of temperature from the Excel files that were collected by the sensor. We can see the window and the interior temperature in case of not having the shutter and in case of having the shutter closed. So those curves are showing the yellow is the indoor window temperature, the blue is the indoor panel temperature, the green is the indoor air temperature. So as we can see, there is almost a 5-degree difference between the panel temperature and the window temperature, like what we are seeing from here. However, in the case of having the shutter closed, you will find that those two lines representing the panel and the window are almost overlapping. So there isn't that difference between temperature, which means that there is a stabilization in the temperature profile when the shutter is closed. In addition to this, why don't we overlap the interior and exterior temperatures in case of no shutter and in case of having the shutter closed? You will find that there is a very large variation in temperature in case of don't having a shutter, like what we can see from here on the curve on the left. So it is fairly large variance in the interior temperature, which we care about. So people wouldn't really feel in this region between February 1st and the February 5th, people wouldn't feel really good sensation of indoor comfort. However, this doesn't happen when we have the shutter closed. When we have the shutter closed, you can see on the graph of the right that the temperature is really stabilizing around 20 degrees, which is within the comfort condition. And although there was a larger drop in the outdoor temperature that we can see from here, however, the indoor temperature didn't really vary that much. In the biggest drop, even here, the temperature variation was less than 5 degrees Celsius or so, which means that the shutter really did a good job in stabilizing the interior temperature. So if we just take the mean and the variation of the indoor and the outdoor conditions, we will find that the interior temperature with the shutter installed is almost 5 degrees higher than the case without shutter installed. There is a little bit of variation and warming of the weather. However, the stable temperatures are very noticeable here relative to the case of having without shutter anyways. So this means that the shutter was very effective and making the temperatures very stable compared to the case of not having a shutter like what we see on those graphs. So this was a really good conclusion for the future work that the students in our program are intending to continue on. So the experimental and simulated results supported our hypothesis. The insulated window shutters reduce the heat loss through the building envelope. It is considered to be a valuable option for inexpensive retrofitting for existing and poor performing windows that might be in different buildings that are around us nowadays. This will support the net zero emission goals that we really care about in different countries. However, it requires more robust testing under various conditions of the climate and for a longer period of time where this data can be calculated. So our recommendations for the future work that some students in our program are trying to do as well is to record the energy load for the shed experiment, also to do further simulation with the HVAC system included. So instead of having a simple shed, we do it on an a residential building or a commercial building, and also to simultaneously test and control the experiment, to have longer testing period with different weather pattern, and also to test the different material for the shutter and its application, and to add an automated hinge system for optimal open and close time instead of doing that manually. I hope that this was interesting to you to hear, and I'm looking forward to any questions that you might have. Thank you so much.